We'll get started with the next topic. We are getting into a very important concept called drag polar. And to understand a drag polar, we need to understand something about lift forces and drag forces, because drag polar is nothing more than a plot of lift versus drag in some non-dimensional sense. So we will talk about this in this particular module, in this particular lecture. Then we'll continue on to other topics in the future lectures. So these are topics in the future lectures, so they are grayed out. So this is the convention that Professor Brian German is using. Sometimes you'll see the number 3310. That's because the precursor to this course was 3310. It did not have the spacecraft performance component in it. They added the spacecraft component and removed some of the aircraft and helicopter component to fit it into 3 hours. So what are the forces that we are interested in? We are interested in the aerodynamic forces on the body, whether it's an airplane or an aerofoil. We are going to be worried about the pressure forces which are caused by the change in the flow velocity. For example, we have seen Bernoulli equation in incompressible flow. When the velocity increases, pressure decreases, and vice versa. In compressible flow, we have a compressible energy equation. When the velocity goes up, temperature goes down, and vice versa. When the temperature goes down, from isentropic flow considerations, pressure also goes down, and vice versa. Then you may have viscous effects which cause shear forces tangent to the surface. Pressure forces are normal to the surface, shear is tangent to the surface, which may decelerate the vehicle, for example, dragging it, slowing it down. So we have two types of forces that we need to worry about. They are not independent. If the viscosity causes the boundary layer to grow, which changes the effective shape of the body, perhaps even cause the body to stall, changes the pressure distribution. Likewise, the pressure distribution, if you have an adverse pressure gradient, that means if the pressure is rising, the boundary layer may get separated. So these are not really two different phenomena. They are interconnected to each other. So one way of visualizing the pressure is to plot arrows. If it is pointing towards the body, it's a positive pressure, the positive gauge pressure. If it is away from the body, that means negative gauge pressure. What do we mean by gauge pressure? Gauge pressure is P minus P atmosphere. That's what a pressure gauge will measure. So if you have if you don't have a P infinity subtracted from it, P is always going to be positive. It's going to be always pointing towards the body. So why does P vary along the surface? In incompressible flow, Bernoulli equation says when the pressure energy goes up, the kinetic energy goes down, and vice versa. So pressure and velocity are changing. When the velocity changes, pressure changes, and vice versa. In compressible flow, you have something more complicated. Cp times T naught equal to Cp times T plus 1/2 rho V squared. Cp times T plus 1/2 just a V squared over V squared. There's no rho. Then when the temperature goes up, velocity goes down, and vice versa. So why does the pressure vary along the surface? Because the body disturbs the flow. So all over the body, the velocity is changing. Now, non-dimensionalization of the pressure is, as we mentioned, gauge pressure, which is P above the atmospheric pressure, divided by the dynamic pressure. This is sometimes called Q. Therefore, this would be called a dynamic head. So this is Q. So on an airfoil, some places P will be greater than P infinity. Cp is positive. Other places negative. Since Cp is non-dimensional, we will also non-dimensionalize the distances. For example, for an airfoil, we will measure the distance along the chord line and divide it by the chord so that it goes from 0 to 1. So this is a picture of x over c, nose of the aerofoil, to the trailing edge of the aerofoil. Cp goes from positive to negative. So very high positive value means P is very, very high compared to P infinity. Negative value means P is less than P infinity. So over a very, very short distance from the nose of the aerofoil, from the front stagnation point, pressure rapidly decreases. Then it starts increasing. So this is what we call an adverse pressure gradient region. On the lower surface, something more or less similar happens, but not quite so dramatic rise, not quite so dramatic fall. Now the difference in the pressure between the upper and lower surface, essentially this area, is a measure of the lift coefficient. How about the viscous drag? Shear stresses are tangent to the surface. Therefore, we should be integrating along the surface. So we would, if you have some knowledge of the boundary layer from our aerodynamics class, this is the slope at the body surface is the velocity gradient. If you multiply by molecular viscosity, that gives you this tau. So once you have the molar tau, you could integrate it all over the body surface. Because of viscosity, right at the body, the molecule come to a complete rest. At the edge of the boundary layer, molecules are moving at the local potential flow velocity. So velocity is changing like this. We saw all these concepts in the aerodynamics course. Now the slope at the wall multiplied by viscosity is called the shear stress. This is the Newton's, when Newton first found the shear stress, he found viscosity times the velocity gradient, velocity over distance. Now, if you have a laminar flow, you're going to have a lower shear stress at the wall, lower drag in general. When you go to turbulent flow, you're going to have a higher shear stress, higher drag. So the region where the flow goes from laminar to turbulent is called a transition regime. There the boundary layer abruptly starts growing very, very fast. All these concepts we would have seen in the aerodynamics course. We are just recapping it here. So the laminar slope, this slope, think of it as this is the horizontal line, this is a curve, slope is this angle, included angle between the y-axis and the velocity profile. So if this angle increases, that means the slope is higher. So turbulent flow has got a higher slope, higher drag is bad from a drag perspective. But stall may be reduced because of the extra mixing of the turbulent flow. So you may get improved stall characteristics in turbulent flow. So you have a pressure distribution and you have a shear stress distribution all over the surface. This is the boundary layer thickness. Boundary layer changes the effective shape of the body, therefore it changes the potential flow. Potential flow or the pressure distribution changes the velocity profile, boundary layer thickness, so these two are interconnected. Coming back to our shear stress, it is tangent to the surface. Pressure is normal to the surface. So when you integrate it, you'll multiply the pressure by the normal vector, your shear stress by the tangential vector. Then you'll get a vector force. Lift is normal to the V infinity. Drag is along the V infinity by convention. Center of pressure is the point where you have a no moment. It's not a center of gravity, which deals with masses. This is you may think of it as a center of pressure. At this point, there's no moment. Aerodynamic forces pass through this point, but there's no moment at this point. Unfortunately, the center of pressure changes with the angle of attack alpha. Therefore, we define sometimes called a aerodynamic center, usually at the quarter chord. At the quarter chord, the pitching moment, nose of pitching moment, is caused by the aerodynamic forces is independent of alpha. So the point on the body where the pitching moment is independent of alpha is called the aerodynamic center. So that aerodynamic center usually occurs at the quarter cord. These concepts we see in aerodynamics course, and we see it here again. Now, if somebody gives you moment at the center of pressure, this moment is 0. So moment at the quarter cord point would be simply the distance between the center of pressure and the quarter cord point times lift. That'll be the moment. So moment is here we are talking about simply in the two-dimensional direction, but in aircraft geometry, you would have a rolling moment, pitching moment, yawing moment of a complete aircraft, as we saw earlier. Now, for a complete aircraft, lift, drag, and pitching moment would be a function of the shape of the geometry, density, velocity, wing area, angle of attack, viscosity, speed of sound. So this is a dimensional grouping. So we want to scale it. So we could test a scaled model, or maybe do an analysis of a CFD analysis or an aerodynamic analysis of a scaled model. So we want to non-dimensionalize all these dimensional quantities. So what do? We non-dimensionalize lift force divided by Q infinity times wing area. We call it CL. Drag is Q infinity. S, our numerator is drag. Moments usually have an area times distance. So you have to put a distance, which is a reference distance. If it's a 2D airfoil, it's a local chord. If it's a 3D airplane, you have to agree on what this reference length is. Is it a wingspan? Is it a root chord? Is it a tip chord? You have to come up with a commonly agreed to definition. Then you base your CM based on the particular definition. This is the Reynolds number. This is the Mach number. We have seen this before. So we could now write, instead of a dimensional number, non-dimensional quantities, scaled body, not an actual body, non-dimensional alpha, non-dimensional Reynolds number, non-dimensional Mach number. Wright brothers realized the power of scaling, so they tested everything in a wind tunnel. They built a small-scale model and computed CL, CD, and CM. The rest of the world was using this equation. That means they were building a full-scale model, for example, a full-scale glider, and they will jump off a cliff and see what happens. Some live to tell the story. Others are written in their obituary in the Atlanta Journal-Constitution. So few loose ends. Lowercase LDM is for airfoil. Uppercase LDM is usually for airplanes. So this is a convention we will use. Some books, some notes, some countries do it differently. So in some situation, for example, when you have a high temperature or high heat rates or parachutes, definitions somehow differ, but we are going to stay away from this. We're going to be talking about aircraft-like vehicles. So this is a pretty good convention that we could use. So we have concluded the section on the forces and moments on the aircraft.